Okay, last time we saw the square root of a times b equals the square root of a times the square root of b. There are extended versions of this, like root abc equals root a times root b times root c. You do need multiplications, though, not addition, for this to work. Essentially, if you have a radical, and inside the radical you have multiplications only, you can split up what you have into as many radicals as is convenient. And so that formula we saw last time and really extended versions of that formula are going to be helpful in simplifying expressions like this, like what's root 25c to the 12th k to the 44. We'll start off nice. I know this one looks a little funky, but there will be some funkier ones. Just to start with this one, let's just use that extended version. And since inside the radical it was 25c to the 12th k to the 44th, we can split that up into root 25 times root c to the 12th times root k to the 44th. And each of those individually, we've actually talked through already. So root 25 simplifies to 5, root c to the 12th simplifies to c to the 6th with no more root written, and root k to the 44th simplifies to k to the 22nd with no more root written. There's no more root written in this line, like where it says k to the 22nd, for the same reason that there's no root surrounding the 5. Root 25 is what's simplified to a 5. Okay, so we just used that extended version. The colors are here to try to help indicate what just happened, that in the extended version of the true formula, we have plugged in 25 for A and c to the 12th for B and k to the 44th for C to split up this one huge radical into the product of three smaller radicals. So just a moment ago, just as a reminder, where did some of this work come from? I couldn't interrupt the middle of the work too much, but we saw just a moment ago that root c to the 12th is c to the 6th, and we also saw that root k to the 44th is k to the 22nd. What worked really nicely about all this was that c to the 12th and k to the 44th are examples of perfect squares. So this principle of splitting things up into perfect squares is going to be one that we keep trying to do. Now this next one looks like it should be much simpler, root 48, but there are actually some complications in this. The thing to do is we would like to still make use of the formula that's at the top. Root a times b equals root a times root b. So let's rethink of 48 as a product. Okay, so we can think of 48, for instance, as 4 times 12. So inside the radical, in the hopes of eventually using the formula that says root a times b equals root a times root b, let's replace the 48 inside the radical with 4 times 12, still inside the radical. Okay, we haven't done anything with the radical. We've just taken the stuff that's on the inside of the radical and replaced it, 4 times 12. And so now take a look at how root 4 times 12 fits the left side of the formula. And so we can split it up as root 4 times root 12 according to the true formula. Root 4 can simplify to a 2. We're not quite done yet here, actually, because root 12, using in the same fashion, it's root 4 times 3, so it can split up as root 4 times root 3. And so the first two that was originally outside the radical is just copied. The middle thing is a root 4, which becomes the next 2, not in a radical. And root 3, well, there's no perfect square hiding in there, so we'll just have to write root 3. This is in the end 4 times root 3. There's a slightly faster way of doing this. So instead of starting with replacing 48 by 4 times 12, which is totally valid, we should try something a little quicker by looking for the largest perfect square, which is a factor of 48. That is, what is the largest number that goes into 48, which is a perfect square. So instead of turning 48 into 4 times 12, the arithmetic is a little maybe more challenging to think of on the spot, but 48 could have been replaced with 16 times 3 instead, because 16 is a larger perfect square than 4. So let's work out the answer having noticed this. So the previous answer works, don't get me wrong, but if you notice a larger perfect square at first, you can save a little time. So root 48 equals root, and then the 48 was replaced with 16 times 3. Now we use the formula that's at the top to turn this into root 16 times root 3, and then the root 16 becomes a 4, while the root 3 has to just be copied. Either way, you have a final answer of 4 root 3, although this second answer is faster. So this one small example with just root a number is going to, let's say, be a template for how we should simplify this type of problem. So when you're given root z if z is itself already a perfect square, then just go ahead and simplify without needing to use the formula. If you know what you have as a perfect square, it was something square, then and just write down that something. If z is not a perfect square, then find the largest perfect square, which is a factor of z, and use the formula at the top. So for instance, given root 200, turning that into root 100 times 2 is faster than turning it into root 4 times 50. Both work, but this is faster because 100 is a larger perfect square factor of 200 than 4 is. So both will work as a first step. Okay, so let's apply this principle. Let's simplify root c to the 12th. Now, the thing is, c to the 12th is a perfect square because 12 is even, right? So root c to the 12th equals c to the 6th, and we're done. What about root c to the 19th? Well, 19 is odd, right? So we're going to have to do something else. We have to look for the largest perfect square, which is a factor of c to the 19th. Now, here's an approach that's going to work. You might say, well, c to any even is a perfect square, so I'm going to split it up as c to the 12th, just based on earlier, that was a perfect square, times c to the 7th. Take a look. This replacement is valid. Remember, when multiplying things with the same base, you have to add the exponents. We're just kind of doing that backwards. 19 is, in fact, 12 plus 7. And you can split this up using the formula. So root c to the 12th times root c to the 7th. Let's see. The root c to the 7th. The c to the 7th inside the radical can become c to the 6th times c to the 1st. And then we can split that second radical. The one that says root c to the 6th times c to the 1st can become root c to the 6th times root c to the 1st. And now we've got these three things multiplied together. And the first one, root c to the 12th, becomes c to the 6th, no longer in a radical. The second factor, which was root c to the 6th, becomes c to the 3rd, no longer in a radical. And then the third factor, which was a root c, that won't simplify further, so we just have to copy a root c. Lastly, this c to the 6th times c to the 3rd, multiplying things with the same base, got to add the exponents, so we end up with c to the 9th times the square root of c. Okay, so this worked, but this is not the fastest answer. And sometimes people do work like this because they just think of whatever even number they want, and sometimes don't simplify completely. Here's the thing. There's going to be a quicker answer. This is just like the numbers version we saw. There's a quicker answer by looking for the largest perfect square, which is a factor of c to the 19th. Now remember, whenever the exponent is even, you're going to have a perfect square. So the largest perfect square factor of c to the 19th is not c to the 12th. It is c to the 18th. I mean, the thing is, every other integer is even, right? So if you have 19 as the exponent, the largest perfect square factor is just one number smaller. It's one full unit smaller. So think of c to the 19th as c to the 18th times c, or times c to the 1st, right? Noting that c to the 18th is a perfect square because 18 is even. Remember, when you have base and an exponent, you have a perfect square just whenever the exponent is even. So here's a faster answer to the previous question. Root c to the 19th, replace c to the 19th in the radical with c to the 18th times c in the radical. Split up the radical using the true formula that when you have the square root of a product, that becomes the product of two separate square roots. And then finally, root c to the 18th becomes c to the 9th, no longer in a radical, and you still have to copy the root c. So notice both of the final answers are c to the 9th times root c. It's just, it was shorter to start with the largest perfect square, which was a factor of c to the 19th. So let's take another example. Root m to the 41st. 41 is not even, but the largest number that is smaller than 41, that's even, is 40, just one unit smaller. So let's think of this as root m to the 40th times m. Then use the true formula to split this as root m to the 40th times root m. And then the root m to the 40th factor will simplify to m to the 20th, no longer in a radical.